We have today here at M&MoCS Professor Berezovski from Tallinn, and the idea is to start a long collaboration with our group. So we will rather talk about fundamental concepts, which should be the beginning.
Okay.
Common discussion. So,
and introduction, and then the title of my presentation is Generalized Thermomechanics with Dual Internal Variables, and I would like to start with my motivation. The motivation means that I would like to describe some kind of microstructure solid. This is usual microstructure solid like concrete. You can see different kind of inclusions in concrete. And then this is more probably more complicated case because it is microstructure of roller ball. This is cast iron. And you can see the flakes of graphite surrounded by ferrite, and this is pearlite somehow. Yeah? And most interesting structure is delivered by shape memory alloys like this copper, aluminum, nickel. This is the martensitic variants, which are coincide to each other, and this alloy display the organized structure. Before we have chaotic description, but just now we have ordered some. But it is also microstructure which exists in the nature. Okay. And the main problem is wave propagation in solid with such kind of microstructure. Why wave propagation? Because wave propagation is a very good diagnostic tool for material characterization. It is a basis for non-destructive testing of constructions. Okay, waves always accompany impact phenomena, and the moving discontinuities in solids like cracks and phase transformation front can be somehow belong to the wave propagation, at least in time scale. Okay? So, to go to the description of microstructured solids, we need to extend continuum description. The standard extension is made by generalized continuum series, which start with Mindlin and Ehringen works in 1940s. Then multi-field theories, which are promoted by Caprice and Mariana, for example. And also there is an internal variable approach, which start probably with Coleman and Gertin paper, and then by paper of Rice, Magen and Mushik, and so on. The main question is the governing equation for this descriptor of microstructure. This governing equation can be obtained in different ways. For example, by phenomenology and or by homogenization, which is done by, for example, by Mindlin and Ehringen, by Caprice. Another possibility is the principle of virtual power, which is started from explicitly written by Germain, but then also followed by Gerard Magen, Francesca Dell'Isola, Paolo Mariana, and other people, of course. And third one is the internal variable approach, which is also start with the Coleman-Gertin paper and then extended. And I would like to explain only this one, because I hope that you at least know what does it mean, principle of virtual power, and also this first approach. I will start with so-called material thermomechanics, and the starting point in this is the so-called Piola-Kirchhoff formulation of local balance laws of continuum mechanics, and here is simply the notation. This is balance of linear momentum, this is velocity and the matter density. This is first Piola-Kirchhoff tensor. This is simply the force, external force. And this is energy, which is kinetic energy and internal energy. And kinetic energy is defined for macro velocity, not micro at all. This is the material heat flux. Material, okay, it is heat flux in some I don't know the real distinction at that time between the special heat flux and material heat flux. It's heat flux up to now. Then we will see what is different. And entropy inequality, it is the time derivative of entropy. This is entropy flux, and this entropy flux in general is more general than this traditional one by means of the so-called extra entropy flux, K, capital K, which in most cases is zero, but it is not the general case, okay? So let's go further, and then we go to the so-called canonical equations, or equations of the material equations, in material formulations of continuum mechanics. It is balance of energy, which just now is written in this form, and so-called H internal is by definition is this one. So it is the okay, I go further and then discuss it, maybe, but the balance of linear momentum is rewritten in terms of so-called pseudo-momentum, or canonical momentum, capital pi. This is Eshelby tensor, and these three configuration of forces in principle. And Clausius-Duhem inequality is rewritten, simply rewritten. This is nothing but algebraic rewriting. The material momentum or pseudo-momentum is by definition is the linear momentum multiplied from the right-hand side by deformation gradient. And Eshelby stress tensor is constructed from the some kind of Lagrangian plus I don't know this tensorial operation, how to say. This is simply the product of two tensors. It is also tensor of the second kind, second order. And material forces are, by definition, this is the explicit space derivative of Lagrangian, like this. This one is simply the scalar product of the external force and deformation gradient. And this one, internal one, is this. And this is not explicit, but implicit gradient. This means that it is by the taking the gradient, we need to take into account all the from which this free energy depend. So, and in the simplest case of homogeneous thermoelasticity of conductors, the free energy is a function of deformation gradient, temperature, and in principle of the placement. And the first Piola-Kirchhoff stress tensor is defined by the partial derivative of free energy with respect to the deformation gradient, and entropy is defined by the derivative with respect to temperature. And signs are, this is conventional things. Here is not minus, but here is minus sign. And if we calculate the material forces in heat source, we can see that all the internal forces are thermal forces. This is taken by thermal forces. This is standard thermal force dependent on the gradient of temperature, and thermal source is dependent on time derivative of temperature. Okay? So then we can write down the canonical equations without body force, which are canonical in the sense that they don't change their structure if we change the in some sense we change the for example the system of coordinates. They are really canonical. So they have this simple form. We have the time derivative and some divergence, and in the right hand side we have heat source or the configurational forces. It is not the real forces, but configurational forces, which means that they cannot be really measured or understood. Okay? Then we go to the theory with internal variables. What we have here, we have additional, the internal variable here is alpha, and we also suppose that the free energy depends on also on the gradient of alpha, which means that this is the weakly non-local theory. Okay, in addition to standard equation of state, we need to define in some sense some two additional derivatives of free energy with respect to this internal variable and its gradient. And then we can calculate the internal material forces and heat sources in this way. First, I would like to say that we introduce extra entropy flux in this way, following the approach invented by Gerard Magen in 1990. In this way, this is the, in some sense, trick, but you can see that this trick don't change the structure of canonical balance laws. But we have here some modifications of Eshelby stress and heat flux. And also we can introduce so-called intrinsic force and heat source, but the thermal source terms were the same as previously, but the modifications are here. So we can see that heat flux is modified by the influence of internal variables. Eshelby tensor is also modified by this, and intrinsic source terms, both for force and heat source, also depend only on the internal variables. So let me go further. And then we go to the dissipation inequality, which just now has this form. And this intrinsic heat source depends only on the internal variable. If our temperature is constant, we simply have only this term, and choosing this term like proportional to the time derivative of our internal variable, we always satisfy dissipation inequality. This is standard choice of the how to say, thermodynamic play with thermodynamic forces and fluxes. And in this case, we always on the satisfaction of the second law. For example, if we have free energy in the form of this, where this means that other variables are not important just now. So if we have the free energy having two terms, one is depending only on our internal variables, and second one only on the square of gradient, we immediately go to the Ginzburg-Landau or Allen-Kahn equation through this theory. So in this case, in the case of choice of free energy in this form, we go to the evolution equation for internal variable in the form of Ginzburg-Landau or Allen-Kahn equation, which is enormously broadly applied to reaction diffusion equation processes, at least. Okay. So just now we have this kind of single variable theory, which finished with this evolution equation, which is first order in time, and we can go further to the dual internal variables, which means that we add some more internal variables. Why we need to do that? We can see further, but just now the technique is absolutely the same as previously. We simply define additional derivatives of free energy in the same way as previously. We modify the extra entropy flux in the same way as previously. We still have the same canonical balance laws in the same form, not exactly the same, but the structure is absolutely the same. And then we go to the modifications like here, and we really modified heat flux by the second internal variables. Eshelby tensor is also modified in the same way as previously, and forces also modified. What we obtain by this way is that in dissipation inequality, in the same isothermal case, we have not one guy, not one term, but two of them. And then we go to the general solution of the inequality in this form, where it is the positive definite matrix, conductivity matrix. And we can simply analyze what kind of matrix we can obtain. If we have antisymmetric case, like this one, we have evolution equations in this form. This is, in antisymmetric case, you see that dissipation inequality is always zero. It's not, no entropy production, yeah? And then In very simple case, when we start with quadratic dependence of free energy of beta, we obtain evolution equation in this form and immediately obtain second order evolution equation for the primary internal variable. This is what we obtain introducing second internal variable. We can obtain in simple case, of course it is simple case, the second order evolution equation for internal variable. And now I would like to go to the generalized continua, which means that just now I simply show you the scheme which is given by Forest. So the continuum medium can be divided in so-called local action and non-local. So non-local theory we don't describe here, and in local action we have simple and non-simple material. Simple material go to the Cauchy continuum, and non-simple material can be characterized by higher order media or higher grade media, like we can hear yesterday. And okay, and then higher order media, this is or Cassira or micromorphic, and higher grade, it's a lot of possibilities, but we stop here by second gradient and gradient of internal variables. And this higher order and higher grade theories can be classified in this way. So here we have only one kinematic variable, and we can take all the possible derivatives, the space derivatives of that, and obtain higher grade series. And in higher order series, we apply additional fields like this one and this one. This is the same kinematic variable, but this one is microdeformation, and this is the gradient of microdeformation. And these two lines can be somehow identified if we apply that our microdeformation is gradient of deformation, standard deformation. We simply go to strain gradient theory, but we cannot go back, you see, only this way. And if we have this identification with the, this is the spin vector, and this spin vector can be identified with the gradient of deformation, gradient of displacement, or deformation. So we can obtain the couple stress theory. So just now I simply show you the Mindlin theory. In Mindlin theory we have classical strain tensor, relative deformation tensor. It is Mindlin idea. This is microdeformation and this is distortion, so we can have the relative deformation tensor. Then microdeformation gradient, this one, and in addition to the Cauchy stress, we have relative stress and double stress in this way. And then we go to the, in the case of centrosymmetric isotropic materials, we can calculate the Cauchy stress in this way, relative stress in this way, and double stress in this way. So you can imagine how many coefficients we need to introduce. But nevertheless, we can Mindlin write the equation of motion without body forces in this way. And this is the evolution equation for microdeformation, which is obtained by the simply introducing of kinetic energy with some kind of micro-inertia tensor. So micro-inertia should be introduced phenomenologically. So these two balance laws are introduced independently. Yeah? So let's rearrange the Mindlin theory in such a way that we consider not the relative deformation but only distortion, and in this way we simply modify stresses. Double stress is not changed, and Cauchy stress take more complicated form, but at that time the evolution equations have the more or less the standard form like we can see in the standard continuum mechanics. So we have the linear momentum. This is time derivative of velocity, and this is divergence of Cauchy stress. And this is also the rewritten Mindlin second order evolution equation for micro deformation. Just now we simply identify this micro deformation with our internal variable alpha, and the evolution equation for alpha was in this way. And if we take this instead of alpha micro deformation tensor, we obtain this kind of evolution equation. And you can see the full identification with Mindlin theory. Mindlin theory introduced this, we obtain this. We don't know these coefficients in principle. We need constitutive equation for that. But the structure of equations are simply the same. So, and what I would like to say that our second dual internal variable theory recover any kind of generalized continuum theory simply by the identification of internal variables with known introduced. For example, by Mindlin introduced the micro deformation, somebody can introduce something else, but still the structure of theory should be the same. This is what I would like to say. And as a conclusion, I would like to say that we are in the main problem is wave propagation in solids with microstructure. This can be calculated if we know coefficients. Okay, so internal variable approach can be considered as power as the generalized continuum mechanics, and we also can take the coupling between micro deformation and micro temperature, but this is the subject of another presentation. Thank you very much for your kind attention.
Look, you have a second presentation.
Yeah, I have it.
So,
If
maybe it is how we discuss, but normally,
in principle, this is much more simpler because it is one-dimensional. This is the theory. But
okay, now I have understood a little bit more, and also Luca, I think this is the most efficient way we have to proceed, because now we have understood.
yes, something.
Now the idea is to go ahead and to try to find a Lagrangian structure inside.
Yes, this was.
Which possible? For instance, I have a question. You have said that you include in your treatment Mindlin's treatment.
In some sense, we recover, not include.
You recover, which means what?
If we have our theory and consider our internal variable, first one, as a micro deformation introduced by Mindlin, we don't need to introduce second balance equation. We simply obtain it, but the structure is the same. This is what I simply say.
So this means that in this particular case, your theory is already variational.
Maybe, I don't know.
It's variational.
This is not.
Whenever you recover midly, you are variational.
Yes, you are right, because this is the not dissipation at all. So in this case, the variational theory and our theory is the same power. No.
So the idea is to try to discover which is the difference between your more general model and Midlin's model, where variational principle can be formulated and where and when dissipation potential must be included, or if there is a difference so big that you cannot recover your theory even adding dissipation potential.
Yes, I agree with that.
This we have to understand. For making clear the point of our discussion.
Up to now, here, just now, the Mindlin theory, variational theory, and our theory is the same because of the zero dissipation.
So thanks a lot.
The coefficients of your theory are unknown as well as are unknown the others.
Yes, the same as in Mindlin. It is.
In this case, you have a procedure to have the dissipation.
First, probably main message, my message, I would like to say that we can derive the evolution equation for the internal variable, but Mindlin need to suggest that it is guess. But in our case, it goes from the dissipation equality, not inequality, but equality, you see. Mm-hmm. The form, not the all coefficients, but the structure of evolution equation, second order. You see, the single internal variables, as I shown, the only first order evolution equation like Ginzburg-Landau. We introduce second dual internal variable to obtain the second order, like in Mindlin. But we obtain it, not introduce some from the sky, you see.
Mindlin introduced from kinematics.
In kinematics, he said that, okay, we prescribe the kinetic energy for microstructure. It is prescribed. It is not from the kinematics. Of course, the Caprice did the same. Simply introduce that there is some kind of kinetic energy in microstructure. We don't suggest that. We simply
assume.
Yes. So it's in principle, like we just now discussed, it is the same power, the same equations in the end. But what is different in this case, particular case of zero dissipation, that we don't assume any kind of inertia of microstructure. It goes from this, from the structure of theory. It should be only the same. No any kind of difference. Not there is no another possibilities for evolution equation in this case. Of course, what is more probably, as we discussed just now, we also have the possibility to introduce dissipation. It's the same way. But, of course, it can be introduced by dissipation potentials also. But you need to prescribe dissipation potentials, like inertia in Mindlin case. We don't need to prescribe. But at the same time, it's also the question of understanding what we prescribe, what we not prescribed. It's probably we also take some suggestions. I don't know exactly, but it is for us at least. It's clear that this theory may be not very powerful, but it goes from thermodynamics. The first thing, we always satisfy the second law. And how we do that? It depends. It's just now it not need to be satisfied because zero dissipation, but if we have dissipation, we need to satisfy.
So Mindlin in non-dissipation case, Mindlin prescribed the kinetic energy of microstructure.
Yes.
And you prescribe the existence of an internal energy, of an internal variable in this form.
No, we don't prescribe. We assume. You see that if we don't know something, what we do usually, we assume that okay, maybe we introduce some additional variable and see what happens. Mm-hmm. Because you see, if you have the hard solids without deformation, you cannot describe this deformation. And you really assume that there is some deformation, in principle, it can be internal variables, stress and strain. You can introduce in the same way as we introduce this one and obtain the same theory. But what is difference? Strain and stress are internal degrees of freedom, which means that they are governed by the boundary conditions. You change something in boundary, for example, displacement, you change the situation inside. Yeah? But in case of internal variables, it's not so. Internal variables are internal in the sense that they are observable but not controllable in some sense.
You have some boundary condition for this?
It is a very special case. When we calculate, we need something. You're right. Yeah. But we go to the formulation of such kind of boundary conditions from the extra entropy flux. We simply prescribe that extra entropy flux cannot appear at the boundary. It is more or less natural. It is extra entropy flux. It is not standard entropy flux. And it depends only on the internal variables. So it cannot be observable at the boundaries. And from this condition, we obtain boundary conditions from internal variables for calculations. But in principle, we don't need it in theory. But for calculations, of course, we have the second order equation. We need at least two boundary conditions in one dimensional case, of course. But usually it is zero. It's simply if they are zero in the initial instant of time, they need to be zero all the time. But we have no any purposes to have non-zero initial conditions for internal variables, because we don't know internal state. You see? So, we apply, in reality, when calculate this, I apply simply 0 for internal variables on all boundaries. But this follows from the principle of 0 extra entropy flux.